pleased to introduce Jonathan Gael from Ether2. Jonathan Gael is the co-founder of Ether2, a universal switch architecture that paves the way to the pendulum swing back to privacy and performance. He comes from a Bell family in northern New Jersey, where he used to run around AT&T's headquarters playing with video conferencing systems that were first employed by his father, Dr. Sidney Gael, who did not like traveling to the Baby Bells after the phone company was divested in 1984. Today, he lives in Los Angeles, which he predicts will become the first digitally secured city if DQ was to be embraced by the entertainment community. He will be presenting a talk titled, Crowdsourcing the Internet of Things, Wi-Fi and TV. Please join me in welcoming Jonathan.
Thanks very much, and thank you to the organizers for putting on such a great day here at USC. So a quick survey. How many of us are watching TV over the air? Yeah, that's not so far from the national average. It's actually 17%, which strangely enough is good news because that's up 2% from the year. So my name is Jonathan, I'm the co-founder of Ether2, and our goal is to commercialize this novel switch architecture called distributed queuing, or DQ. DQ Research has received a lot of funding from the European Union with grants to our Spanish research partners who were participating in schools from all over the continent. But Dr. Alonso at UPC in Barcelona was the first to model DQ switching, first for Qualcomm CDMA networks, and then his proteges went on to model DQ switching for Wi-Fi and just about every other shared wireless network you could think of. They also won awards from Alcatel and Vodafone, of course they're very involved in the EU. And getting through to the engineers, was one thing, but getting through to the business side of the house at those companies has been quite another. So if you ask Bob Metcalf, one of the co-inventors of Ethernet, about Ethernet's fundamental flaw, he'll tell you I didn't know it had one. But the Internet's other luminaries are very clear. This slide. Given the constraints of the existing architecture. And, well, of course, that it wasn't built with security in mind. The point that I think is more important here, though, is that we keep being sold bandwidth as a solution, when bandwidth will never solve an architectural problem. Okay. So it's important to note, for the sake of this discussion, that there are only two kinds of networks. Contentious and non-contentious. And based on these pictures, it's not too hard to figure out which type of network is better at voice and video. There are many differences between how these non-contentious networks operate, but the one thing that they all have in common is that when you want to transmit, that channel is always available. Doesn't matter if it's KTLA Channel 5, Spectrum Cable TV, or USC's classical radio station. The channel is always available. Contentious networks, on the other hand, require something called a collision detection mechanism. Because we don't get a private line like we used to when we just had the phone company. We get a shared system, more like the post office, where every little package of data has an address that has to be looked at, and you consult this massive lookup table of what to do with that packet before you send it out. So now that we can see that a collision detection system is really important if you're going to have that kind of network, especially when your voice is getting chunked up into lots of little packages. In the old days, and I don't mean the 80s, I mean the really old days, like the honeymooners, you would have a telephone party line. And the collision detection mechanism was you were supposed to listen first before you talked. That didn't always happen. Of course, the next CB radio could be considered the first wave of crowdsourced network. In this case, the caller would actually announce his intention to grab the channel, like breaker 19, breaker 19. And that was a collision avoidance method. And what we used here on the web is more like the telephone party line. We gave it a fancy name called carrier sense multiple access, but in principle it's the same deal. Whoever shouts the fastest and the loudest grabs the channel. Everyone else waits. And then the packets try to go through again, and again, and again, until they finally go through, which is obviously a lot of wasted time and energy. So Flagship Genius, our co-founder Dr. Graham Campbell, thinks of a way that you can do both types of networking with one universal near-perfect switch architecture. Now, Dr. Campbell drew this chart in the 90s, and as you can see, all of these CSMA protocols at some combination of users and traffic take it out in performance. In stark contrast, the DQ solution, the actual performance, just hugs that curve of theoretical perfection at all times. So, back in the 90s, the chip speeds didn't exist to run this type of distributed queue network. But the students, under Dr. Campbell at Illinois Institute, could see that cable TV was going to fall into the same trap as all the baby bells. Now, from a telecom perspective, we've been like a one-legged man in an ass-kicking contest ever since, putting in this kind of system. For the cable companies and the phone companies to ride this internet wave, what it meant they really had to do was superimpose all this Ethernet hardware on top of their existing carrier plant. So you're always talking about two networks to move one packet. Then there's the matter of overhead. Overhead is the amount of bandwidth that gets wasted just managing the network. So if you envision a Wi-Fi network as like a 10-minute relay and it's busy, 5 of those lanes are just managing the other 5 lanes, and they're actually closed to cars, which just doesn't seem fair. Then if more drivers wanted to get on that roadway, overhead would go up, leaving less road available for the cars. So it gets even worse. So Campbell's idea was, let's move the buffer from the middle of the network to the edge of the network and see if that eliminates the traffic jam. And it did. So if you've been online for the last 20 years, you've probably been through a few ISDN and DSL modems. Plus there's all the wireless routers that keep getting replaced every time the standard providers decide to play alphabet soup. There's the MD, MAC, okay? So let's be clear once and for all, no amount of bandwidth can solve the problem in the switch architecture. And switch architecture is like any other architecture, meaning you wouldn't build an apartment building on 2x4s and then decide to put granite floors in the penthouse. The same thing goes for burst-to-burst communications and high data rate video communications and putting it on something like the internet, where the end devices don't even have knowledge of each other. They can't see each other. We keep expecting it to get fixed every time we buy that faster router, but in actuality, the football keeps getting pulled up. So with Ether 2, we thought that having a universal, high-performance trusted network, which also solves net neutrality in the digital divide, would be a pretty big deal. In 2010, we previewed in the alpha category a demo, and we won a demo award, which gave us some Silicon Valley street cred. It also led to some big carrier meetings. We presented at the Telecom Council, and all the carriers said, wow, that's really interesting, terrific technology, but we don't make the gear. We're just the network operators. Okay, well, if you could introduce us, and we did. So we met with the Junipers and the Extremes. And they said, well, yeah, we make the gear, but we don't design the comm chips. Okay. So we talk to the Belcoms and the Qualcomms. Yeah, we make the comm chips, but we discovered that there's only two ways that they're going to really be interested in what you have to say. One, either they have to own the intellectual property, or two, you have to be willing to water everything you're doing down by working with standard board. Obviously, those weren't good solutions for us. There's a third way to have a boatload of cash. Your arm didn't exactly slam the door on us. They only told us it would cost $30 million to build the chip. So to their credit, they were including the writing of the protocol specification, but I don't know what the other $29 million was for. Now, it's hard to find someone who can consume all of our white papers and all the simulation studies from over the years and actually write the DQ cookbook. But that's what we did. It's a 160-page protocol specification. Anyone skilled in the art can use it to build an interoperable DQ network. Sometime later, our chief systems architect went to a different company and filed a similar patent that looks very similar to ours. But he probably didn't think we would see ours through to the award, which of course we did. So Ether2 is the company that gets to say whether this technology is open source in the United States or not. Outside the United States, we already put it into the public domain, and we're only really interested in the U.S. market. It went into the public domain when we were published in the SAE Journal. We were talking with GM's Power Alpha Labs at the time, so you'll see a lot of references in our patent to the automotive use case. They asked us to write a security article because they were pretty freaked out after benevolent hackers had to show them how to infiltrate the mission-critical systems of the vehicle and then apply the brakes while the car was moving. The car had always been a closed network, so GM never worried about security before. But of course, on OnStar, it was IP-based, so it's not as if we couldn't see that coming. 2 years ago at the Mobile World Congress, our research partners in Spain, they featured the DQ logo prominently. We're not sure who to thank for the logo. I like the design. But it makes the positioning of that logo look as if we compete with all of those other technologies, and we do not. This is not the case. In fact, DQ can be inserted into any of those other technology stacks. Even older devices, which have no knowledge of DQ switching, will get a performance boost. This was proven in a 2009 dissertation that modeled Wi-Fi with DQ switching for mobile ad hoc networks. And ad hoc networks are just networks that can be created on the fly, where you don't need to have pre-existing infrastructure like cell sites. That would be cool. So let's say your car ran 2 or 3 Wi-Fi antennas. It would just form an ad hoc network directly with other cars. And, think about the number, big number that comes along with having all these cameras and sonar and every other sensor on that vehicle to try to physically sense the environment around it, as opposed to just seeing the other vehicle on the network. When TUSET demonstrated the first DQ network for the Internet of Things, he won an IEEE award. As you can see from the numbers, we're not kidding when we call DQ near perfect. The packet success rate over 98%. His demo used a Zigbee radio, but he could have modeled it for any of the physical radios on that chart. And remember Dr. Campbell's CSMA chart from the 90s? Well, if we zoom in over here for that poster on the right, in this case they saw no point in plotting the curve of theoretical perfection because of over 98%, the actual performance for just a little bit right on top of it. So if your company is on an IoT mission, these would be the features given our switching that would be afforded to that type of product you're trying to build. I like what they put at the top too. I couldn't have said it better myself than CTT said that distributed queuing is a revolutionary technology that will change the way wireless networks operate in the future.
Can I have a question?
Sure.
A lot of it is on the network side, right? How expensive it would be with the data transmission over the network? Are you guys making that easier or less cost, less effective?
Well, let me explain where we are now in terms of the networking itself, because there have only been 2 experimental networks built so far. The first one was on the Zigbee radio in Barcelona. The next one we'll get to in a second is from Bucknell. But this has not been built out commercially yet. We've had 2 academic experimental networks that demonstrate the switch architecture itself. They've both been in the IoT. The reason I'm giving this talk today is because we want to get out of the IoT. You know, we want to move into the higher data rate antennas like Wi-Fi and 4G. But if your project could take advantage of any 1 or 2 of these bullet points, you'd have a pretty big leg up on the competition. Being able to take advantage of all of these bullet points, it's not even a contest. In terms of energy savings, to be a little more specific, Barcelona engineers found that the IoT networks they were building were only working half as hard as the other IoT networks that don't use distributed queuing. And that savings of energy is just based on the elimination of retransmitting packets over and over. It says nothing about any of the other savings we can afford, such as eliminating the asynchronous hardware from Cisco, or if you were Netflix and you wanted to shrink your streaming footprint, well, use a broadcast architecture, because all the while you can just take users as they're coming onto the network. You hit them with a staggered spot of advertising, but in the background, all you're doing is you're camping these users onto a single channel, so that you can transmit once instead of transmitting 10,000 individual streams. I mean, if TV had a day of streaming, it never would have come off the ground in the 1940s. So, set patent. So 3 years after we filed in 2012, which was shortly before we were being published in the SA Journal, we were awarded the first applied research patent. The second link over here goes to the subsequent patent, submitted by our esteemed colleague on behalf of another company. But the reason I'm posting it here is because I don't care if it's our patent or not. I want engineers to be able to see how Barton was thinking and what ideas he put in the patent that he wrote for this next company that he worked for. So last year we were honored to take part in the Innovation World Cup at the Mobile World Congress. An international jury of 20 engineers selected our technology in the security section, simply because security is a function of packet efficiency. So we're not really a security company, but a DQ network could never suffer from the security problems that the net has today. So I'm in Barcelona for the event, and I get an email from James Ballard, who's here at the Blackstone Launchpad at USC. He says, "Hey Jonathan, this RFP came across my desk from Google. Sounds like it's right up your alley. You guys should apply. Send me whatever you got, I'll push it forward." I looked at the RFP. It was co-authored by Vint Cerf. I said, "You have me at Vint." You guys know who Vint Cerf is? He's one of the co-inventors of Internet Protocol. So I've been quoting Dr. Cerf, for a long time, because he's the authority. And what he says here is we take a broadcast radio like Wi-Fi and we turn it into a point-to-point link. Okay, so what he's saying is everything that comes out of that antenna in that phone, in your pocket, it gets broadcast. It's already being physically broadcast. It's already going in every direction at the same time. But we forced the network to use terrestrial thinking, like Ethernet, where it can only see every device it can only see every device as a point-to-point link. So it sees every device, even though it's wireless, it sees it like it's still connected by a wire. And then of course he goes on to say we just don't have protocols that do that, even though the underlying communications services are capable of delivering it. Well, that's why I'm here today. I'm here to let you know that that's no longer a true statement. There are not protocols that can do that. So this is what it looks like when we get a Google Research Award. They were supposed to send us beacons, they were supposed to send us on-hub routers, they were supposed to send us Edison chips for our graduate students here at USC. We got the beacons, we got the Edison chips. We didn't get the on-hub routers. We called up Google, we said, what gives? And they said, well, both of our OEMs for the on-hub router pulled out of Google Research. So we were a little flustered, a little mind-boggled. Our mentors in Spain, who were looking forward to working with the kids here at USC, I shouldn't say kids, graduate students, and also at UC Irvine, you know, everybody's just wondering, what do we do now? It just seems so strange because on one hand, you've got Vint Cerf and 260 other internet engineers, you know, writing an open letter to the FCC in 2015 saying you have to embrace open source principles. We need better security and Wi-Fi, and for that we need open source Wi-Fi. And then on the other hand, you've got the OEMs who make the Wi-Fi router pulling out of Google Research. So that was a little odd. Part of me thinks they just didn't want the grad students making a better product than the one they were going to market with. So this year, another ray of sunshine from Bucknell researchers who used the Barcelona demo as their starting point, and they built a test bed in Philadelphia. They used the LoRa radio hat instead of the Zigbee hat. It's that little card with the white antenna sticking out of it, and that card is sitting on top of a Raspberry Pi mini computer. Together, they form a low-cost base station for the IoT, and they used Adafruit modules for the edge devices, and again with our switch architecture. For the DQ code itself that K.E. Zhang built at Bucknell, it's on GitHub. So what they found at the end of their study was that a single base station could cover 95% of the city. Now that's the radio property, that's nothing to do with us, that's just physical radio coverage, but it is pretty good. The part that we lent to it with our switch architecture was that with a 30K per hour upstream constant, we could still provide support for over 5,700 of these Adafruit devices. The further conclusion that they drew was that if you put one of these base stations in every city of the state, you would be able to have a long-range IoT network that covered 99% of the population. In 1993, going way back, when DQ was first published for cable television, the Navy was looking at potential multicasting solutions. As you can see, DQ switching was categorized as dreaming. Again, the chip speeds didn't even exist. Since then, the research has been conducted at schools all over the world, and obviously chip speed is no longer an issue. One of the earliest simulations in cable TV was from Georgia Tech. And what they found at Georgia Tech was that even though the homes are geographically dispersed across the network, each device on a DQ switch was seen at the same exact distance from the head end. So everybody on the network is getting the data at the exact same time. Now imagine what that would mean for something like high-frequency trading, where these brokerage houses try to game the network by getting their servers as close as physically possible to the exchange servers. Well, if we guarantee that everyone's going to get the data at the exact same time, you can't game that system anymore. After the $80,000 study, Scientific Atlanta named the DQ collision technology in their 1998 cable TV patent. They never licensed it because DOCSIS was chosen as the cable TV protocol, and the 802.14 working group was disbanded. It's now a dead working group. But if you're a cable TV customer, you know that you've got a cable TV modem or a DOCSIS modem, known as a set-top box. You also know that you've got an Ethernet modem, which is known as an Ethernet modem. Again, you're running the two networks to move one packet, which just has never made sense to me. So let's look at over-the-air TV broadcasting. The FCC asked TV stations across our country to rescind their right to manage the frequencies that they're no longer using, now that over-the-air television is digital. The mobile carriers have been salivating over these frequencies for a very long time. So the FCC decided to run what they call an incentive auction. Now, does anyone know what the incentive is? A portion of the billions of dollars of proceeds that they're going to reap at auction goes back to the TV stations. So, what exactly was meant by this television code? Well, it was a code of trust, because the broadcasters were given the right to profit and, sell advertising space, so that they could manage those frequencies, and in return the broadcasters serve the public with content, with entertainment, with educational programming, and real news. Now, in what world can the trust manager decide to abandon that trust, say it's okay for it to be liquidated, and then take a portion of the proceeds? Make no mistake, they're taking the airwaves that belong to the public and selling them to companies backed by subscribers. So, fortunately, over 1,000 of the TV stations in our country did not participate. And this tells us that those stations are looking for a better solution. They want to keep serving the public. So is this the solution? It may look like a web, but in actuality, when you zoom in really tight on any one of those individual networks, it's a star configuration. None of those devices on that network can talk to any other device on the network without that router in the middle. So for the entertainment business, where content is king, do you want the network to look like a star? Or do you want it to look like a web? Because these types of networks can be created for content, for voice, for Internet of Things, and of course for regular old web services like email. Again, just like over-the-air TV, except with the ability to create a theoretically infinite number of channels. Finally, we can migrate to a wireless data network that actually gets stronger as it gets larger. Now, DQ, our distributed queuing switch architecture, can do for switching exactly what Linux did for serving. I mean, it's going to reduce the cost of all that expensive switching gear to a commodity box, which is how Linux ate Microsoft's lunch in the data center. We'll want to, of course, use the best TV frequencies that are currently not in use by TV stations. Why? Because they are the very best frequencies for distance and building penetration. And so I asked you, what's more important, a cellular subscriber or a firefighter? And the answer is pretty clear. Who should get the better frequency, when they're behind concrete in a burning building? And so, I don't know, it may not sound legal to undermine the FCC and all the carriers, but I don't think Uber or Lyft asked for permission before they decided to start crowdsourcing taxi services, which went against a lot of different laws. No, and the reason it didn't matter is because the public voted with their wallet. So, Ether 2 is no different. We're really just taking something and trying to get it from point A to point B without the archaic radio dispatch system. So for TV stations to become more important pillars of community once again, there's more than 17%. And to have a way forward in general, technocracy just might be the only way to evolve from this two-party system of corporatists. They create fictitious bodies with free speech and unlimited capital, and it is certainly not what the framers had envisioned. This is why, in my humble opinion, nothing could be more important than showing the public what their publicly owned airwaves can actually do for them. If you're like me, I don't like paying for air, and we wouldn't have to if we ruled the air. For example, I'm here, my wife's on the west side. We're probably 2 or 3 hops away from each other through DQ hubs. And these DQ hubs would just be credit card sized devices that are plugged in somebody's home. That said, I'd also love to design a firmware upgrade for the central office system with the AT&T and Nortel switches and turn those into IP switches. Why? Because then you could just plug in a Wi-Fi hub at home in the wall to that old phone jack that you still have there, and guess what? During a power outage, your Wi-Fi would stay up. Amazing, right? I mean, that's big. Everyone's got cameras now at Nest, right? What happens when the power goes out? So, our URLs are parked at GoDaddy for now. Until we're capitalized, we're not going to spin our wheels with any more awards and routers that don't show up. Perhaps we can try crowdfunding at some point, or maybe somebody here in the audience knows an Eli Broad or a Zuckerberg or maybe a George Soros. Anyone who can help us create the first virtual Bell operating company without actually having to build the network, because the public would be doing that for us. Then again, DQ networks can happen with or without a governing authority. And maybe that would be a good thing, especially in countries who have regimes that like to kill the net every time people start acting on democratic principles. So no, we're not a security company, but I'll be happy to address privacy or any of these security issues. Thanks very much.